G'day guys, in this particular video I'm going to be showing you a polar coordinates example problem. A plane is being tracked by a radar. At the instant shown, theta is equal to 120 degrees and theta dot is equal to minus 0.05 radians per second. Find the speed of the plane if it's swooping out a path given by this expression just here. So what's going on? We've got this plane and it's swooping out this parabolic path just here, and it's being tracked by this radar, which at this instant is at an angle of 120 degrees from the horizontal. So somehow we need to figure out the magnitude of its velocity vector, which is always going to be tangent to the path, v, using this information. So the game plan here, and this is the way I'm going to solve this, the game plan here is we want to deconstruct our velocity vector into our radial, this is our unit vector in the radial direction, er, and our theta direction like this. This is our unit vector in our theta direction. If we deconstruct our velocity vector into these two components, we can use the polar coordinates formula to help solve for v. That's the game plan. Okay, let's get started. The first thing we're going to want to do is we're going to try and figure out where this plane is relative to the radar. So we need to figure out where this line intersects with this parabola. So let's draw that up here. Let's draw our parabola, and let's draw this line which shows where this plane is. This intersection will be where our plane is just here. Well, what's the equation of this line just here? Well, if this is 120 degrees and our radar is at the origin, that means the equation of this line is quite simple. You can prove this using rise over run formulas. It means this equation is going to be y equals tan 120x. That's the equation of this line just here. And we already know the equation of this parabola, it's given to us, so now we can find out where they intersect by simultaneous equations. So let's do this. Let's substitute y out from both of these equations and solve. We know that tan 120x is going to be equal to minus 0.003 x squared plus 4,000. Right? And this is a quadratic formula we can solve, so let's put these two guys on the left-hand side, and we're going to be left with 0.003 x squared plus tan 120x, which is minus 1.73x minus 4,000 is going to be equal to 0, and we can solve this using the quadratic formula, and we already know what the answer is if you just plug in minus b plus or minus the square root of b squared minus 4ac over 2a, and that's going to be minus 901 meters. That's one solution to this quadratic, and the other solution is going to be x is going to be equal to 1479 meters. Okay, so we've got two roots to this quadratic. Which one do we care about? Well, let's think about it. The plane is clearly to the left of our radar. So this clearly corresponds to a negative number. So this is clearly the value we're interested in. This corresponds to this. This positive root corresponds to if we were to continue the line here, it would intersect with this parabola underneath the ground. Clearly that doesn't concern us. Clearly the one of interest is this value just here. We can solve for the y-coordinate of our plane at our instant by plugging in x is equal to minus 901 into this equation or into this equation. So let's do that. Let's plug into this one because it'll be easier, and we can prove that y is going to be equal to 1560 meters. So far, so good. We've found the position of our plane at this instant. Now, at some point, in order to apply the polar coordinates formula, we're going to need to find the radial distance, right? We'll need to find this distance, which is called r, from here to here. And we can do that by using Pythagoras. We know it's going to be equal to the square root of x squared plus y squared, right? Which in this case is going to be these two terms squared added to each other and square rooted, which is going to be 1800 meters, right? That's the distance from here to here. So far so good. We've found one term which we can use for the polar coordinates formula. What do we do now? Well, now that we know where the plane is, we can also find the gradient of our curve at this instant, which will help find us the direction of our velocity vector. Remember, velocity is tangential to the path, so if we find the tangent, we can find out the angle the velocity vector's at. So let's do that. Let's begin by differentiating this equation. We know that dy dx, and I'm just going to write in a different color, is going to be equal to minus 0.006, right, when you bring the 2 down here, x, right, and this constant goes to 0. So dy dx is going to be equal to this, so we can solve for our gradient at our point just here, which is going to be, when you plug in minus 901, it's going to be 5.41. So we've found the gradient of our curve at this point, and this helps us find the angle of our velocity vector, because of course our velocity vector is always tangent to the path, right? So let's draw our velocity vector just here. We know it has a gradient of 5.41, which means its rise over its run is 5.41, which means that the angle from the horizontal gamma is going to be given by tan gamma is going to be equal to 5.41. You solve for this, you solve for gamma, and gamma is going to be equal to 79.5 degrees. Okay, so you've solved for gamma, which gives you the angle of our velocity from the horizontal. Okay, so far this is amazing. We found out the angle of our velocity vector just by using geometry pretty much. Okay, now what we're going to do is we're going to deconstruct this velocity vector into our radial and theta terms. Okay, so let's draw this in here. This right here, what I'm drawing right now, is going to be our component of velocity in the theta direction, which I will call v theta. And this right here is going to be our velocity in the radial direction, which I will call VR, right? We know that this angle here, from here to here, is actually 30 degrees. And if you don't believe me, let me show you why that's the case. This is 120 degrees, which means that this must be equal to 60 degrees, which means that this must be equal to 60 degrees, which means that if you were to continue this e theta along here, this would be 30 degrees, which is the same angle here. This is 30, this is 30, okay? And to be 100% sure, to not confuse you, this right here is going to be v theta, and this right here is going to be VR. This is VR, this is v theta. That's all I'm doing. I hope I'm not confusing you, okay? And the beautiful thing about doing that is now we have the angle between these two things. So we know that this angle here is going to be equal to gamma minus 30, okay? Now that we have this angle, we can solve for VR, we can solve for v theta. So let's do that. We know that VR is going to be equal to V times by sine gamma minus 30, okay? Likewise, we know that V theta is going to be equal to minus V times by cosine gamma minus 30. Now, why is it minus? It's because the theta direction is actually this way, but I've drawn the velocity vector in this direction, so it's got to be negative, okay? So now that we've got VR, now that we've got v theta, we can use the polar coordinates formula, which states, and let me draw it for you in case you've forgotten, it states that the velocity vector can be written as r dot er plus r theta dot e theta, okay? This is the formula we're going to use, right? And you might be thinking, well, how do we apply this formula to what we've got here? Well, VR is the velocity in the radial direction, which is r dot. And v theta is the velocity in the theta direction, which is r theta dot. We just equate these two guys together. So let's equate these two first. We know that minus v cosine of this is going to be equal to r theta dot. So let's write that down. We know that r theta dot is going to be equal to minus v cosine of gamma minus 30, right? Now we know what gamma is, we know what theta dot is, it's given here, and we know what r is. We can solve for v, and that's just standard algebra, so let me do it in one go. That means v, our velocity vector, the magnitude of our velocity vector, our speed, is going to be 138.6 meters per second when you solve for this guy just here. And you can also show that this is the same thing as 499 kilometers per hour. This is our answer, okay? Now, just to briefly summarize, what we did is we deconstructed our velocity vector into our theta direction and our r direction, and then equated using these formulas and solved for our velocity, solved for our speed. we could have also found r dot by equating this term with this term if we wanted to. Hope that made sense, guys. Cheers.